So, hello everyone. Welcome to week 6 of the TT sessions. So, if you have any doubts, so we'll mostly be covering these neural network based topics. So you can uh, write your doubts in the chat, or you can unmute yourself and ask.
Hello, this is Bhushan.
Hi, hello, yeah,
This is Bhushan.
hi,
I
hello.
want to ask some basic questions
Hmm.
on terminology.
Okay.
One is, in the beginning of this course, we learned about features and parameters and hyperparameters.
Yes.
So in neural networks,
Hmm.
is the number of neurons equivalent to the features and weights equal to the parameters? Is this a correct thing to think?
Uh, no, that is not actually correct. So let me explain. Uh,
Why I felt this way, because ultimately you are getting an equation w1x1 plus w2x2 plus b, that
yeah,
is the
right.
function.
Hmm.
So I thought that the same thing you get in b transpose x. So I thought w1 are the weights, are the
The
parameters, and x the
weights,
features.
yeah, the weights, the W1s are the parameters. However, you cannot say that the number of neurons are the number of parameters, because each W, suppose you have this neural network, right? Say you have a 3 here and a 2 here. So this will be connected. Suppose it is connected in this way. So suppose suppose this is a three-dimensional vector that you have, two-dimensional vector that you have. So there are in total 6 weights here: W11, W12, and up to W32. So there are 3 sets of weights. So for each set of neurons, you have. So suppose your this layer of neuron has some m neurons. So this layer has m neurons, and this has your n neurons. Then these these weights can be represented by a matrix which is of dimension n by m. So for this simple case, we have nm parameters. So parameters are the things that you can learn. The learnable variables are the parameters. Now when coming to hyperparameters, so as you know, in a neural network, it is up to the user to decide how many layers does the user want, how many neurons in each layer does he want. So this decision, so changing the number of parameters, changing the type of activation function, all those things are the hyperparameters, because the user can change those to get different results. So it depends on the choice of the or the type of problem that you have. And coming to features, so suppose I think in the first or second lecture we saw the example of these house prices, right? So for these house prices we had like area area of the house, the uh, the year or the age of the house, location of the house, and so on. So these things are the features. So you use these features to learn some model. So while learning, what you do is you learn these parameters. And how do you improve your model? You improve your model by tuning these hyperparameters. So in a neural network, so suppose we have some neural network, suppose it has one hidden layer and one output layer. So this input that you give, so it will be connected like this. So this input that you give, these are the features that you have. The number of parameters, so these are there are 3 here and 4 here. So you have 3 by 4, or you can say 12 parameters here, and here again you have 4 parameters. So the first layer of the neural network are the features, these are the hidden layers, and this is the output layer. So
Okay,
let
the
me show
number
you.
of neurons in the hidden layer are not features.
The number of, so actually you can say that it is a type of feature that you have learned. So suppose suppose these are initial image that you have given, or suppose you are given some initial data. So then you apply some weight and go to some state of, suppose you are at some state. So in some terminology you can say that you have learned some features, but these are not the features or the actual features of the data that you have been given. These are some of the features that you have learned after updating these weight parameters.
Okay. So these features are artificial features which you have created.
Yes, these are some intermediate features that we have learned. So basically it is like your neural network is given some features. Your neural network is learning some intermediate features to get to the output. So like
Okay.
in kernels, what we did was, so if you remember kernels, we are in some lower dimensional space. So we went to a higher dimensional space so that our program becomes, or our problem becomes easy to separate linearly. So when we went to higher dimension space, that was not the original features that we have, but the some features learned by the net or the model in that case. So this is analogous to that example, these
Okay.
intermediate features.
Okay. Okay. Thank you. I have another question on global minima.
Uh,
We are using, they said that in gradient descent, you can use batch gradient descent or you can use stochastic gradient descent, and there are certain advantages and certain trade-offs. They said that in stochastic gradient descent, you can jump over the local minima. You don't get stuck in the local minima. I want to know, is there any way of finding the global minima? That is first question. Second question is, global minima always lesser than the local minima? What is global minima?
so, hmm, so suppose I give you a loss. I suppose I give you a, suppose this is a function that you have. Suppose it is a function. So this is your x, and suppose this is your fx. So here you can see. So let me change it a bit. So here this is a minimum point that you have, right? Out of all the points, this is the lowest point of the function. This is the lowest value of the function. So this is the global minimum. So out of all, so global minima is the point of the loss. So whenever you are working with machine learning models, the loss are generally in some sort of a curve. So in, suppose this is some curve, and this is the minimum that the loss can get. You cannot go lower than this, right? So this is known as the global minima. So this is the best that your function can do. So when we talk about, yeah, so the other question was, can we always find a global minima? So
No, how do you
finding,
know? How do you know if you find a minima, it is global or it is local? And can we find a global minima?
so suppose your function is like this, right? So now it is easy to see that this is your global minima.
Yeah.
So this is possible for certain type of functions known as convex functions.
Okay.
If you have a convex function, you can always find the global minima. It is always. So how do you know it's a minima? So the derivative at this is zero, right? The derivative
Yes.
at this point is zero. So convex functions will always have one minima, and that is itself the global minima. However, this is a non-convex function. So in non-convex functions, as you can see, the derivative is zero at this point. However, it is also zero at this point. It is also zero at this point, and I think these points. So these are all, according to the algorithm, it can say that it is. So concentrate on if you concentrate on this region, say we are looking at this point. So in this place, this is a minima, right? However, this is a minima locally in this place,
Hmm.
but in the overall scheme of things, this is not the global minima. So even this is a minima locally. Even these are local minimas. But yeah, if you are running some algorithm to find the minima, so it is possible that you can get stuck here, because your algorithm will see that you are at a place of zero derivative or zero slope, and it will assume that you are at a global minima. However, that is not the case. The global minima is actually this. So it is not easy to find the global minima, because in some cases there can be a lot, almost uh, huge number of global minima. You do not know the form of the function. If your function is something of this sort, you cannot know which one is the global minima from the local information that we have. So many neural networks type of algorithms, they work well when you are at the local minima. There is no need to go to the global minima, because then it is a very hard problem to find this problem.
Okay. And is batch gradient more accurate than stochastic gradient?
So accurate in one sense, you mean?
I mean, see, you people. I mean, ultimately, our job would be to find
Yes.
the best
It's
gradient descent. You know, I mean, the best
yes.
gradient descent.
Best parameters.
Now,
Yes.
yeah, best parameters. Now, it may be possible that you're using batch gradient, but the computational cost is very high, time is high,
Yes.
because okay, in local it may not be that high. Okay, but so I'm not talking in terms of computational cost. I mean, in getting the quality of parameters. Is batch gradient superior to stochastic
Okay.
gradient?
So in a sense, you can say, but there's a trade-off, right? In batch gradient, you are looking at a large amount of data, and then you are creating, choosing a direction to go into. So you can say that you are having more information when deciding which step to take or which direction the step to take. But in stochastic gradient, you are only considering one point. You are only taking a direction by having the information that what is the gradient of the loss function according to this point. But so suppose you have 10,000 points, and you are in one epoch. So epoch is like uh, one epoch. So one epoch of trading, like you look at the full trading data once. Suppose you look at the full training data once, and you are at one epoch. So because, and suppose you have suppose 10,000 points. So for stochastic gradient descent, you will update your parameter 10,000 times, right? Because each time you take a gradient, you will update the parameters. So 10,000 updates to the parameters. But if you are doing batched gradient descent, and suppose your batch size is say 100, so your updates will be like 100 updates to the parameters. So because you are using more data for calculating the derivative for batch gradient descent, you will have a more so your noise or the direction in which your data will go will be better compared to your stochastic gradient descent. However, stochastic gradient descent also has more number of updates. So in general, batch gradient descent works better because, yeah. So the best is the your full gradient descent when I use the full data. So stochastic gradient is when you use only one data at each point, and batch gradient is just in between these two. So yeah, batch gradient descent will perform better than stochastic gradient descent, but you cannot say whether the batch gradient descent will go to a global minima or not. It all
Okay.
depends on the loss function and where you start.
Okay, in this example which you are given, could you just in this example which you are given, you said batch gradient descent batch 100. What is this 100 epochs or 100 are the
No, no.
examples?
And so you have 10,000 points, and in batch gradient descent, what you do is you create batches. So you create batches of equal sizes. So if I say that one batch has 100 data points, so you'll have
Okay.
100 such batches. So like in SGD, we're taking one data point at a time and then doing the gradient descent. So in batch gradient descent, we look at one batch at a time and then do the gradient descent. So in that way, we'll have 100 such batches. So we'll do 100 such updates to the gradient descent algorithm.
And in each batch, how many examples will be there? What? 10,000
So
data points?
so you have 10,000 data points, and you are dividing it into 100 batches. So
Okay.
each batch will have 100 points.
Okay.
100 per.
In the lecture, this is called mini batch gradient.
Mini batch also. So yeah, so batch, yeah, actually batch is the when you look at the whole complete
Whole,
data.
whole. Okay.
Yeah. This is actually the mini base, right?
That's what I got confused.
Right.
Okay, thank you. Thank you very much. Thank you very much. Hello.
Hi. Hello.
Nobody is asking. So can I ask another question?
Yeah. Sure.
See, in this exercise, what they have shared asked was, different types of errors. Like, mean square, we understand. What is this binary cross entropy and multi-cross entropy? That is not explained anywhere in the lecture.
Okay.
But that question has been asked.
So, have you looked at softmax laws? So I guess softmax has not been covered.
No.
So first of all let's look at binary cross entropy laws. So we see in logistic regression, right? Uh, so in logistic regression, our objective was to so suppose given a pi, sorry, so your objective was to p to the I 1 minus p to the yi. So your objective to maximize was this quantity, right? So if we take the log of this, we have taking the log, we get y log p plus sorry, this 1 minus y log 1 minus p. So what happens? Uh, suppose your suppose p is your probability of belonging to. Suppose you have two classes belonging to class 0 or say class 1. P belonging to class 1, so it is p and this is 0, yes, and 1 minus p is a probability of belonging to class 0. So whenever your suppose your y is 1 and p is a probability, so your probability of belonging to class 1 is will be log p. Otherwise your probability of belonging to class 0 will be this probability, right? So this is called a binary cross entropy loss, because suppose you are saying that your probability of belonging to class 1 is high, but your actual target label or actual target label is say class 0, then it will try to minimize this. So your objective was to minimize this cross entropy loss. So if say probability of belong to class 1 is high, so then your log p will be high, but suppose your y is 0 in that case. So in that case, this quantity will be a large quantity and you want to minimize those. So this was the binary cross entropy loss for two classes. So you have classes 0 and 1. So when we talk about multi-class cross entropy, this concept is extended to the multi-class. So suppose you have classes 0, 1, 2, say we have some C classes. So your objective becomes minimize I from 0 to C, y or class C, say y equal to class C log P of uh, log P is the output that you are given, and yeah. So this is an indicator vector which says that whether your class belongs to YC or not. Sorry, class is I. Whether your object or your data point belongs to class Y or not, and log P. So this is a multi-cross entropy loss. So basically the thing is, you don't need to know the details. This is applied for two class problems. This is applied for multi-class problem, classification problem, and your mean squared error. So your mean square error is given as y minus f of x whole square, half of this. So this is a loss used for regression. So these are some commonly used loss functions in any of these machine learning problems.
Okay, so BC and MC is used for classification, and
Yes,
the other for regression.
regression.
Okay.
There's actually minus and here.
Okay, many a times there is some confusion about how do you decide how many layers you are going to have, and how will you decide how many neurons you are going to have in each layer. Are there any thumb rules, some guidance, or what is it?
So so basically, actually that is a hyperparameter tuning. So in the sense, it is just you have to experiment with some experiment with different values for the number of parameters that you want, number of neurons that you want. But in some sense, suppose you are dealing with images, and suppose your image has some small points like small circles. Suppose this is your image, and using something like CNNs, we have some idea like we need a kernel of this size, we need a kernel of this size in order to capture this. So it depends on problem to problem, like how much information that you want to capture. Again, this is a purely trial and error type of thing, but
Okay.
that is yeah, depends on what type of data that you have. Even in
Okay.
languages, say, so you have a language or you have a sentence, and you want to see like what are the nearest words to it. So sometimes you will say that, suppose this, you have some word here and you want only the previous word and the next word, -1 and +1. Sometimes you will require more than these words, so it depends on the type of problem that you have.
Okay. Okay. This convolution networks are a separate class of neural networks, so it is completely different from forward propagation.
No, no, no. Convolution networks. So intuitively, we say that we have some image, and then we have some filter, you can say, and then we move this filter across this image. But if you try to look at it in the form of a neural network or the original neural network design, so you see, suppose this is your image, and suppose it is an m by n image, and suppose you have a kernel or a filter of size, say, 3 by 3. So you're moving this 3 cross 3 kernel to all of these patches, right? So you can say that if you convert it into neural network, so your first layer will have uh, mn number of neurons, because that is the number of pixels that this image has. So
Okay.
then you are moving this 3 by 3 kernel to each of these. So suppose I will maximize this. So suppose you had some 3 by 3 image, say, and suppose you have a kernel of size 2 cross 2. So in this case, your kernel will be at this position first, then it will be in this position, then it will be in this position, then it will be in this position. So you can see that these pixel, they get the kernel covers the most of the times. So if we convert it into a neural network,
Mm-hmm.
so you will have 9 neurons here, because 3 by 3, and these so you can see that, suppose these are 1 2 3 4 5 6 7 8 9. So your, suppose this is your kernel or the convolution layer. So this 4 this pixel 4, it is with the one kernel 1 and it is at kernel 2. So suppose you have this 4 here, it will be here and it will be here, but it is not. So this 4 is not connected to the kernel that we get when it was a 3. So it will not be connected to the rest of this. So this convolution, in a sense, it makes, so earlier you saw that your neural networks are all is fully connected, right? But due
Okay.
to this convolution, because of there is the sharing of this kernel, we say that there is something called parameter sharing. Your number of connections in the next layer decreases. So
Okay.
if, so earlier, if this was say m, this was n, we would have say mn number of parameters earlier, but now since this decreases, the number of parameters will also reduce. So this is one of the advantages of CNNs, that even with less number of parameters, you have more optimal number of parameters. Not optimal, but more efficient in size of parameter size and calculation. But it is also able to extract good features to learn. So
Okay. In this example, you
mhm,
have put 9 in the first layer. That is the
yes,
input layer.
yes.
How many will be there in the second layer, which is the hidden layer?
So it depends how many you want to
You are
take.
doing 2 by 2. K is equal to 2 by 2.
K is equal to 2 by 2. So then, so let's see. Uh, yeah, I will create a new image here. So suppose this is your K. So earlier we had 9 here, and now so this, so let's number these 2, 3, 4, 5, 6, 7, 8, 9. So with K1, so this is your kernel. With K1 we have 1, 2, 4, and 5. So suppose we have K1. So if 1, 2, and suppose 4 and 5 will be connected to K1. So it will be fully connected in this part. So then once we get to this one, we'll have more different set of neurons. So 2 and 5, 2, 5, 3, 6 will be connected to this, but 1 and say 4 will not be connected to this. So that's how we get the sparsity. Is that clear?
Okay.
So it also depends, like sometimes mostly we use more than one features, more than one kernel. So right now I'm using only one filter or one kernel here. Sometimes we may use more than that. We may use 3, we may use hundreds of kernels. So this depends on how many kernels that you are using.
Okay. But so my question is this: what you did now, is it called convolution or is it called
Yeah.
pooling?
This is a convolution.
And what's the difference between convolution and pooling?
Okay. So what we're by convolution, what we're doing is we have this kernel window, right? This red kernel window. We have this red kernel window, and we are moving this. So first it will be here, then it will be here. So convolution is basically moving a kernel and computing it. So suppose our kernel is, suppose this is our kernel. This is a 2 by 2 kernel. Suppose each of these values is 1, and suppose this is the image that we have. Suppose you have a value of say let it be 1, 2, 3, 5, 6. So when the kernel is at this point, so what we are doing is we have this 1, 2, 4, 5 patch, and we are having this 1, 1, 1, 1. So basically multiplying each of these with this one. So because these are all ones, we'll have 1, 2, 4, and 5. Suppose you had 2, so this will be this. Suppose you had 2, so let's make this different. So this will be 2, 4, 8, and 10. So after we move this kernel to each of these different positions, now our image will look something like this. So we had 2, 4, and because 2 will come again, I think it will be 8. So 3, it will be 6, and 4 will be done a few more times because it will be here, it will be here, so maybe it will be 16. So it will have different values, right? Even here, let's say it is 10. So this is what happens after we do convolution. Now when we do pooling, let us look at for pooling, let us look at this patch. So you have this 2, 8, 16, 10. So now instead of keeping all of these, what we do is we just, maybe if we are doing max pooling, so we say max pool, we'll just separate or just represent it as 16. Just say the this block, instead of this 2 by 2 block, we'll have a 1 by 1 block, say 16. Or if we want to do something called average pool, we'll just take the average of this 2 plus 8, 10, 10, 20, 20, 36. So average is I think 9 here. So instead of this 2 by 2 block, we'll have a 1 by 1 block. Say we're doing average pooling 9. So similarly, instead of this, we'll have some block. Instead of this, we'll have 1 block, and instead of this, we'll have 1 block. So earlier your image was 3 by 3. Now your image becomes 2 by 2. So pooling, it tries to accumulate each of these local information that you have, and it accumulates them in, we get a lower dimensional representation or an image of lower size. So that is the difference between convolution and pooling.
Okay.
Thing is a downsampling.
Yeah, pooling is like a downsampling. Yes.
Sir, I have just a query regarding the assignment. Again, the wordings are they not clear? Like in one of the that auto encoder is similar to PCA. What do you mean by similar here?
Which
Hello?
question?
I don't remember the number, but it is a question. There was auto encoder regarding question number 9, I think.
Okay, okay.
Yeah. So
Oh, the L.
last time also the hard margin is used for the zero. That I'm sure. And soft margin, we come to the picture where we introduce the tolerances, but they have answer is A. I marked a D. So what is the, but clarification? I am not satisfied. What do you want to give?
Okay, so for this, so we know PCA is a dimension reduction algorithm at once.
Means PCA could be used as a hello. Hello. Am I audible? Hello.
Yes, yes, you're audible. So, yeah. Yes, go on.
Hello.
Yes, yes.
Okay. That PCA is I read somewhere. It is a single layer auto encoder we can use either. Like both are doing the job, but okay, that is also ensure that auto encoder could non-linear if you are using other
Yes, so
encoding.
PCA is also, so you have a PCA, so you can go from a higher dimension to a lower dimension.
Lower dimension, yes.
So when in autoencoder, you go from a higher dimension to a lower dimension. Now, I cannot exactly answer this question, but I think you can make the connection there. Right? Whether it is
No, just the similar word means
yeah.
as a job we are expecting here and what functionality
similar
they are
means,
serving, or
yeah,
the
not the
because
output,
one could
but
be a subset of superset. One autoencoder is a superset and PCA could be a subset.
It's like right. So similar in the sense that techniques for dimension reduction, whether they are the same or not.
Okay, thank you. And what regarding the earlier that hard margin and soft margin regarding that question?
Let me look.
In the previous SVM question number, I think 3.
What do you mean by hard margin? Okay. Classification.
Actually, my doubt is regarding 0 is considered as a low here. That's my point that point of doubt.
So the original
Like
the original definition of SVM is actually this. The original definition is said to be the max margin classifier.
hard and soft margin is general term, not only related to SVM. I think fuzzy system we do use.
Yes.
That kind of yes.
So the original that we have, that is termed as a max margin classifier that we have. But when we go for so in soft margin, we were allowing some slacks, right? So suppose this is your positive plus, this is a negative plus. We're saying that if this is your margin, some points could be here, or your red points could be here, even it could be here.
Yes.
So these all depended on the penalty term that you choose. So if your penalty is very high, we require that these terms, we do not allow these type of noises, right? Because we want to reduce the number of errors in that case. So hard margin is like your you just you want you do not want to allow for this type of, you want your margin to be say something like this. So this is your hard margin. We do not want errors in that case.
Neither. Yeah, that I understand the concept, but answer is how it is a answer should be D, no? That's why.
Okay. That's very low error in classification. Plus
Low word means we are allowing some tolerance. But zero is there is no allowance.
So as you can see, the A and B are
So
actually
A statement should be wrong, not a, this
no,
should be
A
checked.
is right, like because we do
Why
not
zero? No, there is a difference between zero and low. Now, low could be zero is a subset, but here hard margin we are defining as exact. There we are not tolerating any kind of error, right?
yeah. So
So zero error is that, and low margin, if you are allowing low
mhm.
or little bit tolerance, then it's soft compute, soft margin. It is followed.
Yeah,
That's the concept of zeta
it
comes here.
yeah. If you yeah, based yeah, it is some
No,
terminology.
exactly. I
So
wanted to know the definition, how hard a margin is defined in a like IEEE definition we should follow, or that's the
yeah,
only
that
the
is
concern.
actually this is a bit vague in that case because the terminology which should have been different. Because if
Concept
you
is clear but from my side, but that's the only terminology wise how we.
so I guess the question setter was like it
Uh,
depends on how much error. So if your penalty is very low, you
no,
want
but
your
in technology again, terminology we are giving some norm that there has
uh,
to be definition, should be
yeah, yeah,
well
yeah,
defined. Should not be
yeah.
ambiguous. That's why
I
we techniques we develop the language as this. Apart
mhm.
from normal natural language,
Yes, yes,
natural
yes.
language has ambiguity. That's why. Okay.
Okay.
Sir, can I answer that one?
Yeah, sure.
Yes, let's give it.
Yeah. See, if you're able to convince, it's okay. Just I'm giving my explanation actually, what I understood. Okay.
Hmm.
Yeah. Sir, can you open that figure? The question paper, can you open? No, 5. That
Okay.
same assignment question, can you open?
Wait, let me share my
Then
screen.
that figure, the first figure will give that little idea.
Hmm. So which one do you want?
Assignment 5. Same
Assignment
assignment
5, right?
5. Yeah.
Okay. Let me share my screen.
Yeah. 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 Here,
Hmm.
I'm just taking the example of the question number 1.
Hmm.
See, really in practical, there is no the soft margin or a hard margin. The zero error is not possible practically.
So
There will
yes,
be
so
some
this is a soft margin. We can
yeah.
consider as a soft margin. Yeah.
No,
Hmm.
whatever the soft or hard margin, the zero error is not possible in practical. Okay, it will be some error will be there. Some the like they say yes, the blue color is there. No, that's called the out. That is the noise basically. Understood? No. So if you see this figure, we can do the hard margin here because it's clearly classifiable, and there is the vectors are not there in the margin place at all. Okay, so we can have the clear cut. So this is a hard margin. Okay, however, there will be some error will be there because there is some very low error will be there. Okay, now you take some other figure which madam showed where there is a overlap will be there, very close. You can't put a exact margin. Okay, so such cases we go for a soft margin. Okay, so we allow the more errors basically. Okay, so whatever is the question they
No,
ask now.
low and high doesn't make any no sense. Low and high, we have to be concrete in definition.
No,
Like
no.
I,
Now,
if
now,
Fuzzy said, I think hard computing and soft computing come this picture. No? Hard
no.
we have
So
particular
uh,
Swiss threshold.
See,
so
this picture
the
is seen now.
hmm.
Here is hard margin you apply, correct? No, you understood, no? Or low margin. Yeah, here which one you have to explain? Hard or soft?
If you gave other even there is more outlier points like there, then how we will say that
See,
there is
outlier.
only one we are
No, no,
able to see, but it's not in practically could be more.
no. Outlier is not there in outside. Suppose where you apply soft margin, you see that the
What blue
margin is
point is
shown.
from this point, I'm saying that there could be over 2-3 more points then.
No problem. But still, you apply hard margin. Your error will be low. Now you see another figure. Madam showed one more figure where
Then it
no.
is not hard margin. That's I'm saying that it's a hard. How it is a hard margin? If there is a error, then how it's a soft
No,
margin
so
concepts come into that picture. No soft margin. Then what's
so
the difference?
yeah. So let me. So
other figure,
my
sir. One more figure
interpretation
is
is
there. Yeah,
so my
just one more.
interpretation is that this
Hmm.
hard and soft is it's just a relative term. So if your this error penalty is less, we say that it is hard. If your is giving less and less slacks, otherwise it is a soft. Or else if you want a zero error, that is termed as the max margin because that is the most optimal margin that you have. Otherwise, you will require some error. And how much error you want to give? So that depends. So if you're allowing some small amount of error, you have a hard margin, or you can say harder margin. And if you are allowing for more leniency, so you can have a softer margin. So the question setter, I think, was looking for
Can we
this.
have anywhere reference of this clearly well-defined hard margin definition in Word where we can find it?
Let me see.
No, in Google, there are different, but some standards definition we have to follow somewhere.
Excuse me, sir.
Yeah, sure.
What are activation functions?
Oh, activation functions. So give me a few minutes. I'll get back to you. I'm actually looking for a book.
Okay, sir.
Sir, that
Most of all the concepts are there in statistical signal processing. The ML is just introducing a terminology. It has just the name or the little. That's why I get confused.
yeah,
I
sir,
want to
can you
know.
open the slide? The 33, that whatever madam given, no, the slide number 33. With that, I think you can able to explain easily.
Okay. Okay.
I'm
Let
just
me see.
comparing that.
Anyway, you can send it later on also. Not a hamper. But I want some standard definition which we could follow.
Yeah. So basically, the ideal case is referred to as a max margin classifier, and then we go for these hard and soft definitions after that. So, yeah. So you can
So what is the
ask
again
this.
overlapping word? Then overlapping, how we are? Will we call in question number 1 overlapping points?
So these are, we can allow for some soft.
Slide
So
number
one
33.
point is here. So can we say it is overlapping or not? Whether these data are separable or?
Sir,
So
slide
data
number
is not.
33 open. Slide number 33 open, sir. Then we can VC for it.
Okay. So in this example, your data is not linearly separable. You cannot draw a line and separate these points.
So we will say here it is overlapping, right?
Yes.
1 point.
Yes, this is an example of overlapping points. So which page number?
33. 33.
Yeah, this one. So yeah, this is an example of overlapping points. So yeah, what was your? So Jitendra, you were saying something.
Yes, no, I didn't find yet the hard margin definition. Yeah.
Okay.
This is clear. I get it.
Okay, so
we can't apply a hard margin, am I right?
Yeah, we cannot apply a hard margin here.
Yes.
We have
Then
to allow for something.
there's a clarity. I'm just thinking that like.
So yeah, this confusion is basically a mix-up of because of no ambiguity in what is hard, what is max margin. I think that is the confusion here.
It is similar to fuzzy like concept or derived from hard and soft value.
Yes,
So
yes.
then hard is means hard thresholding. There is in equation, it should satisfy. There is no tolerance we allow. In soft, we handle the tolerance a little bit either. We can.
Yeah, right.
Anyway, I will also explore some other that if you have
Yeah,
some which book follow, then that will be better. Later on also you can say, we should not
yeah,
waste time. Okay.
yes, yes. So there was a question on activation functions, right? So coming to activation functions. So why these neural networks work is because suppose you have some layer here, then you have another layer here, and you have another layer here, suppose, and then you have an output. So suppose this is your X. So suppose you have no nonlinear activations. So then you can multiply this by some weight matrix Wx, say W1x. So suppose this is your H1. Then your H2 will be W2H1, and your H3 will be your W3H2, and this is your output. So let us look at what is H3, right? So H3 is W3H1, which is W3H2, which is W3 W2H1, which is W3 W2 W1X. So H3 can be written as W3 W2 W1X. So this is same as suppose we multiply these matrices together. Suppose this is some W. So we can say that your H3 is Wx. So this is same as saying that you have some features, or you have some input layer here, and you have some output layer here, and you are multiplying this some matrix W. So these two models are same because you're not applying any non-linearity. We can say that this is same as a single layer network, but then we lose the power of neural networks because we know that neural networks learn uh, functions, can learn non-linear functions. So that is why we introduce this non-linearity. Now if we have these non-linearities here, say we are using some sigmas here, so basically, so as you saw in logistic regression, we have this logistic or sigmoid function, right? So this, what it does is basically uh, you have, this is your 0 and this is your 1. So basically it, whatever value that you give, it squashes your value to 0 and 1. So suppose uh, your activation at this point is say H1 is W1X, right? So then you say your activation 1 is we apply sigma on top of this. So this could be any number, right? This could be any real number. It could be 100, it could be 1000, it can be minus 1000. But when we apply sigma to this, you get a value between 0 and 1 in this case. So activation functions are used because that is what makes these linear networks powerful, and also because if you just use these neural networks with just some linear function, this same as learning linear regression, because this is a linear regression model. You want to make it more complicated, so these are said to be these activation functions to make your neural network learn more nonlinear functions. There are other types also, like there you have 10H, you have ReLU, and so on. Is this clear?
Sir, so just to confirm, so it is the activation function which causes neural networks behave non-linearly, correct? Without
Yes.
activation, it becomes only linear.
Yes, right.
Right. Okay.
So we are basically making the model to give any probability value so that we are using activation function.
It need not be probability. So your sigmoid gives values in 0 and 1. But if we talk about ReLU, so ReLU is like, suppose this is your x. If x is less than 0, your value is 0. If x is greater than 0, your value is x. So ReLU is defined as maximum of 0 or x. So this is the type of ReLU. So you do not need it to be to output some probabilities. Like 10H will give an output between -1 and +1. So we do not get an exact probability type of thing. We just have some non-linear type of function. We require this non-linearity.
Why would we need this non-linearity?
Can you repeat?
Why would we need these non-linearity in functions? What help does it?
Okay. So let us look at a XOR example. Right. So this is 0. This is 1. This is 1. This is this. So I think your XOR had like at 0 0 it is 0. It's 0 here, and you had 1 here. So if you just use a linear function is like we cannot draw some line like this to make these linearly separate these two. So when you use non-linearity, like the one that ma'am said, so it learns some. So you require some say decision boundary which is like this. So all the points which are inside this decision boundary, these are positive, which are outside, these are negative or 0 in that case. So these non-linear boundaries are learned using these activation functions or these non-linear functions that they have. So these help in learning functions such as this.
Oh, okay, sir. Thank you. One more time. What is the difference between convolution and recurrent neural network?
Convolution. Come again?
And recurrent neural networks. Recurrent neural networks.
Okay. So when you're talking about convolutions, so in CNNs, what we have is we are given some image and we have a set of filters and we move these filters across this image. Move it here. So this movement of this filter across this image is what is said to be a convolution. So this is useful for why do you need this? Because suppose we have a picture of a car here. So my drawing is not good, but yeah, we have some picture of a car here, and these are the windows. So we want to say that suppose we are looking at this point. We want to preserve the information that this will represent an edge of this type, or if you are here, this will represent an edge of this type. So these are called as spatial information. We or you can say that this is a different type of edge and so on. So if you want to preserve spatial information that how these images are, how this type of these objects are present in space, you use this convolution type of operations. But suppose you have a sentence, right? Going to RNNs. Suppose you have a sentence, say he is going to school. So here, suppose we look at the word going. Suppose you look at this word going. There is no concept of these edges or anything in this word. What we want is like what word appeared before is, what word will appear after going. Sorry, what word appeared before going, what word will appear after going. So we want to preserve this order of uh, the words that are coming and going. So recurrent relations, these recurrent neural networks are helpful in capturing this type of information. That is why if you look at recurrent relation, there is this hidden state and there is this state from t-1 at time, and then they output what is the output at the next step. So this is the basic difference between CNNs and RNNs. Of course, you can use CNNs for text, you can use RNNs for images. Yeah, this can be done, but you have to do modifications to it. But in general, this is why they are designed. Is that clear?
Yes, sir.
Sir, the same question.
Huh.
Can you tell me one more thing? During filtering, no? See, there are two
Huh.
things. One is filtering, that means that convolution activity. Then the pooling activity, okay? The pooling activity is very clear. It is reducing the things. It is making the reduction, but preserving the features, basically, okay? But during filter time, you're processing. So basically, what type processing will do? See, one is we're doing the like 2x2 or 4x4. You will select it, okay? Then pooling time, we'll do reduce that 4x4 to 1x1, whatever. But in that 4x4 itself, you've done some processing. Last time you then multiplied some with some factor, and so what process done during the convolution in addition to the making the filtering?
Okay. So so let us look at this image itself. So suppose this image will have some, so because this will be dark, so this will have some high values. Say we have some 100 here and 100 here. So this, we are looking at pixels. So these are dark pixels, and suppose this will have some white background, so it will have a 0 value, and this will have some other color, so say some 65 or something. So if you are looking at a pixel like this, so suppose it looks like this, and suppose we learn some convolution on this. Suppose our convolution is say um, 1 minus 1 minus 1 minus 1, say. So then you get something like 0 minus 100 minus 100 minus 65. So this your short means after applying convolution.
Yeah. I have not understood how you got that 1 minus 1. What is your that there are
Oh,
only like last time also.
okay. So this, so as we saw, this convolution operation is also applying a neural network. So these are actually, these values are actually learned. These are also parameters. So instead of this, I can write W11, W12, W13, W14. These are parameters that are learned because you want to teach the neural networks. So which feature do you want to capture and how much importance do you want to give them? So these weights of the convolutions are also learned during the backpropagation algorithm. You do not set it manually. Is that what you're asking?
Yeah, clear. That's clear now.
What is the meaning of this word flatten, which is used in one of the examples? Examples means assignments, but it
Okay,
is
so
not.
yeah, so if you look at neural networks, it is like you have some vector type of input layer, and then you have this hidden layers, right? So, but suppose you have an image of this sort, it is an M by N image. So you cannot pass this image directly because we need a vector of this type. So what we do is, suppose this is your row, suppose this is your row 1, this is your row 2, and this is your row M. So what we do is, first we make this row 1 into a vector. So suppose this is your row 1. Then we append this row 2 below row 1. So this is your row 2. And so on, and at the end you will have row M. So earlier it was an M by N matrix. Now you have a Mn dimensional vector. So now you can use this vector and pass it into a neural network like this. So this process is called flattening. Is that clear?
That means every layer we will flatten and then I'll give the input. Is it like that?
Yes, 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 right. So that is why you apply convolutions to this. So this mn will be large. Like suppose your mn is 1000 by 1000. So if you give a 10 to the power 6 dimensional vector as input, it will be very complex, right? So that is why you apply this convolution, you do this pooling, so that your size reduces a little bit, instead of this 10,000 or this 10 to the power 6.
This word forward propagation, I just want to clarify. Suppose you have a one hidden layer network, and say first input layer has 2 neurons, hidden layer also has 2 neurons, okay, and say output layer has say 1 neuron. When you use the word and the forward propagation, you are doing say W1x1, W2x1, and then using an activation function and getting an output, which is an input for the hidden layer. So what is the definition of forward propagation? When you just calculate W1x1 plus W2x2 plus B, or you put this into the activating function, and what you get out of the activation function, that is called forward propagation.
So this whole process is forward propagation. So here we'll do W11x1 plus W, because you are having this your information here, and you are just going from this layer to this layer. So at this layer you have this summation W 1I xi and sigma of this. Then again you will go from here. So this direction you are going is the forward direction. So that is the forward propagation. Backward is like you are having these errors here and you are going back. So this is the back propagation.
Okay.
That means in the forward, this one we will not calculate the errors.
No.
The accurate will be not there.
So
Correct.
the process is, first you get your data, you do a forward propagation and you get some output, right? After you get some output, you calculate your errors and do back propagation. So now your weights, this W1, W2 will be updated. You'll have new weights. So using these weights, you again do a forward propagation. You get a new set of so first you had suppose Y had one. Now you get a new set of output labels. So then again you calculate the error and then you back propagate. So it goes on like this until your error becomes 0 or you have some other stopping criteria.
I have one more question.
Yes.
In the exercise, no, whatever exercise is given to us, unfortunately, it was done up to the training the model, but not shown the example for the validation or the final prediction. Okay, the tutorial was there up to validate this one, fitting the model only for the neural network, whatever example given. So, is it possible for you to explain that one? I can with the prediction and is possible?
You want the code?
Yeah, I think we did not give the code also. We didn't got the
Yeah.
code because the link was not given there.
Okay, okay.
And the second one, it was given up to the fitting the model. But the validation data is not used and prediction also not done. The giving the random also not done. That's one
Okay.
part. And one more question I'll ask in the same thing. It is for basically the digit identification. Okay, 0 to 9. We'll classify
Yes.
it. Okay. Now I have a small question. The final output layer, there are two possibilities there. The one is it can give an output of one vector of 9 features, because y can be a multi features basically. Okay, so it can be a one vector with the 9 features. With that, only one is activated. Like if digit is 8, 8th index is activated. The way input is given. Okay, or
So
yeah, or it can be 9 output with only one is there. Okay, so how it will be the real, what is the difference between these two approach?
So basically, when you have a multi-class type of problem, so this is recognition. Sorry, digit recognition is generally this MNIST data set. So here we have 10 classes, right? 0, 1 up to 9. So in these cases, what we have is this softmax layer at the end. So you have this neural network. This is your input. These are your hidden layers, and this is your output layer. So this is a softmax layer. So softmax layer basically looks like your e to the power, suppose say theta, and summation e to the power theta I by summation e to the power theta j for j equal to 1 to, suppose you have 9 classes, 9. So basically what the softmax layer does is it gives you a set of probabilities. Suppose your example is of class say 5. So in this case, your fifth class will have the highest probability, say 0.9, and other will have less probability, say 0.01, 0.002, and so on. So when you do a maximum or argmax of this vector, you get that the maximum value is, or maximum, the class with the maximum probability is 5. So this is how you handle multi-class classification in neural networks. And the loss function related to this is the multi-class cross entropy loss that we covered before. Multi-class cross entropy loss to calculate the error or and do back propagation in this example. Is this approach clear? So what you're saying, that is also, that can also be done. So there is, you must be familiar with this one hot. So one hot is nothing like, but suppose you have 9 classes, so you have 9 such ones, and suppose your class is 5, so you will have a 1 at 5 and 0s at everyone else, and so you will try to predict the value 1 at this. So this can also be done, but this is the more popular approach that is done.
Okay, so in the same thing, the input, the whatever the label data was there, no? In example, when they said the label data is 1 hot, okay. So the output will be as 1 hot, or it will be, if I use the softmax, output will be it can't be different, no? When I do prediction, what I mean, the label data which is given x and y for me, the y is basically 1 hot, okay.
Yes.
Now when I do prediction, finally, when I take the model, the prediction, if I use the last layer softmax, then it may not be the 1 hot. It will be like this, whatever this one, what you given.
Yeah, it will give the, suppose, yeah, if it is correct, you will get class 4, else you'll get some other class.
So the neural network I can training with one approach, but the prediction I can do with the another way, correct? That means if I train with the 1 hot, but I can do the prediction with the last layer with the softmax output layer.
You can do it. So even if you output a 1 hot, you can just check there is numpy.where function where x equal to 1, and then it will give you the index where you have a 1 in this case. So this is just a post processing step that you can do to extract the label that you have.
Okay. So it's all depend on the output layer how I am writing the kernel. I mean
it all depends.
softmax or whatever I used. Okay. Okay.
Yeah, but mostly people use softmax because the loss function here is very easily differentiable, and there are some nice properties, so that's why it is used.
Okay. Thank you.
So coming back to the question of hard margin, so there's a book by Christopher Bishop. So that is a classic book. So you are right. So hard margin is generally when you don't allow any error in our case, so 0 errors. Else we say that it is a soft margin. So I think you are right. I mean, you are right. I don't have to think. Yeah. But the question was, yeah, bit. I think bit ambiguous in that sense.
If others doesn't have some questions, I can have some questions on SVM. Some slides.
Yes.
Can you the slide number 24 of SVM? No, I have got some confusion there.
Slide
If somebody has question, let them continue. So if nobody has question, we'll see. SVM. This is a previous class, no, not yeah. I think.
Let me share my screen.
The next previous week. This is the last week. I am in SVM.
Yeah, this is the SVM slides. 24 is this one. Are you referring to these slides or what is the topic?
'24. Can you go to 20? Is 25?
Yes.
Yeah. Here the theorem. That's this is alpha or beta or it is A star. I have the theorem. That word, no, that line. Can you? Is it? It's alpha beta or it is? I got confused with that. What is A and B here? The last line.
Oh, this one. Yeah, these should be alpha and beta, your optimal dual variables.
Yeah,
Yes.
yeah. It's not A and B, am I right?
No.
Okay. That I was trying where the A and B has come from there. There's one more thing. And okay. And slide number 53.
Yes.
53, yeah. This one. I have one some confusion. Xi, Xj plus B. Yeah. This basically for the prediction. When we have the X value.
Yes.
So how where it is X? Here we are not at all giving the X. So
No. This should be X. This should be X.
I got confused. Here also I was breaking my head. Where the X? I'm not getting the X. So I thought, okay, maybe somewhere I missed it. Right? I was not getting. So it is X only, correct?
This is X, yeah.
And Xi is the support vector. Xi is the support vector.
Xi's are the support vectors.
Support vector. Yeah.
With respect to this alpha, yeah.
Yeah.
Non-zero alphas.
Exactly. That's one more. That is 50. So that's clear now. And in the logistic regression, the first, can you go in the logistic regression at the beginning? Logistic regression, the last one, no, the end of this slide. That means the logistic regression last. We are able to predict the value. Then can you go slowly? Yeah. This one. How we calculate the alpha value? How we'll find the alpha? Or it is like random? We select how?
Let me check.
Like beta plus alpha.
Oh, acha. Alpha is like So we have seen gradient descent, right? We have this beta or alpha, the learning rate parameter. So here they are doing gradient ascent. So in gradient descent we do we go to the minima. So in gradient ascent we go to the maxima. Alpha is similar to your that is a learning rate actually.
Oh,
So
same
it is a
methodology.
hyperparameter.
Ah, okay.
Yes, that is the same one.
And the start of beta is some random. The B0, the beta 0 will be some
Yeah,
random.
we give some random value, maybe all zeros, maybe all ones. It does not matter.
Okay. Okay. Slide number 22 has one more doubt is there. That KKT condition was there, no?
Uh,
Yeah. Here,
this one.
no, go back. Can you go back, sir? Yeah. See, yeah. Here in the duality, we have the condition here. G of W is less than or equal to 0, or H of W is less than or equal to 0. Okay.
Is
But
equal
whereas
to
equal, sorry. So whereas our requirement, no, that condition of the line is greater than equal to 0. So is it applicable for all the rules, or it's I've got confused there. It's not
so
exactly.
then
Yeah.
yeah. So you had right yi and yi into this should be greater or minus one should be greater than equal to minus one. I think conditions are like that. So you can take this minus one to the let's say and minus of this would be less than 0. So it is just algebra. You have to do some move manipulation to write your equation in this form.
Okay. So I tried that way. Can you go next slide? Next slide. It is there, I think. Next slide, and it was. Okay, no issue. Yeah.
So
Yeah.
yes.
Yeah.
So you can bring this one to this side and you multiply by minus one on both sides. Then you have say one minus this less than equal to 0. You can write it like this.
Okay. So finally your transfer, like, yeah, I bought the one in this side, then I didn't multiply,
Uh-huh.
so I got confused. Okay, no issue, I
Uh,
understood. Somehow you have to make to that one equal to other one mathematically.
yes, yes,
Yeah.
yes. You have to take it, bring it in this form.
Yes. Okay. And one more doubt here. That next slide. This duality will hold if the primal problem is max and min, ulta, the reverse. Is it duality hold?
Mhm.
No.
So this one, yes, this one, right?
The primal problem is max and min. Then
Uh,
is it always hold?
uh, no, can you repeat?
Here the primal problem is min. Then first you find the max, then become the min. Okay.
Yes.
Now assume the primal problem is reverse,
Hmm.
max and min.
No. Then it
Then it
won't
will
be
not. Yeah. Okay.
because
Yeah.
you can think the your primal is something like this. So you're trying to minimize the primal, and your dual is coming from below. So you're trying to maximize the dual. Like
Geometrically it will not hold. I understood. And I
yeah,
do
yeah,
geometry, I can see.
yes. So if your primal was like max and min, your dual might have been min and max because minimizing one and maximizing other should be the same or the other way around.
Yeah. Okay. Thank you.
Okay.
Your voice is missing. I can't hear your voice.
Hello.
Yes, now it is.
Yeah. So, is there a question?
I have a small query. When before the exam, the last week, when we have the session, so that no, we read everything and we have the doubts clearance can be done.
Yeah, we planned for this, so I think we had a plan to do that overall
Yeah.
session. So I think we will have one.
So that maybe that week 24th means that 19 or somewhere it will be there. Am I right?
Yeah, yeah,
So
yeah,
that there we can ask the questions from the any slides, correct? No, the entire.
yeah, yeah. So we had a
Yeah.
plan for that. So I think it will be done. It will be announced at
Oh,
discussion, but most probably we'll have that.
oh, thank you.
So if there are no more questions, I think we can leave the meeting. There are, yeah. Otherwise, we can discuss if there's anything to discuss.
Hello, sir. In AI
Yes.
and ML, what are the basic mathematics we should be prominent in learning? Because
Oh,
I attended very few sessions, so that's why I couldn't able to follow as the others could follow. But I would
okay.
like to know what are the basic mathematics on which
So,
topics we should be very much prominent.
so you should have some knowledge of linear algebra. So these matrix vectors, their decomposition of matrix vectors, low ranks, and all those type of things. So on basic course in linear algebra will be good, and you should also have some knowledge of probability. So those are the main things: linear algebra and probability, and some calculus and
What
basic
will be the
calculus.
in-depth one, huh?
Yes. Uh, so for linear algebra, you can find some courses online, even for probability, and some basic calculus. So like finding the maxima, minima, and all those type of topics. And also, if possible, you can go into this convex optimization, but that will be a bit tough to get into. So I think linear algebra, probability, and calculus will be enough to understand some of the basic algorithms in ML.
Thank you, sir.
Just one question on convolution. I'm just having a doubt that convolution does not reduce dimensionality, or does it?
No, convolution does not reduce dimensionality. It reduces your number of parameters to be learned, because you're having this shared pixels, right? So due to which the number of weights that should be learned, that thing is reduced. Number of parameters is reduced. Does not reduce the dimensionality. Pooling reduces the dimensionality.
Pooling reduces dimensionality.
Yeah, right.
Okay. Okay. And okay, and flattening is completely different. It need not reduce dimensionality. It is just
No, no.
adding, just
You're
adding up
making,
the.
yeah, you're just making your image or your matrix into a vector. That is just the flattening.
Okay. Flattening and softmax is more or less same. Every softmax function flattens.
No. Flattening is just a representation. You have a matrix and you want to write. You are like stacking the rows of the matrix on top of the other to make it a vector. Softmax, it suppose you have a multi-class problem. You have some problems. Suppose there are 10 classes.
Okay.
So softmax gives you a probability. So what is the output? So the output is what is the probability that your example belongs to a given class. So suppose your example belongs to class 8, that probability will be highest. The less of the probability will be low. Softmax gives you a probability distribution, which says that what is the most possible class for the given data. So these two are different. Flattening and softmax are different.
Okay, suppose you have one 3x3 matrix. How do you flatten it? Just by putting the one column on below the other?
Oh, so 3x3 means you have 9 elements, right?
9 elements.
So suppose you have a vector of length 9. Your first 3 elements will be the elements of the first 3 rows of the matrix. So those are your 1, 2, and 3. Then you'll have 4, 5, 6, 7, 8, 9. So your 3x3 matrix will be a 9-dimensional vector in that case.
And it will be first 3 rows. First 3 rows of the vector will be
row wise.
It will be row wise.
Yes.
Okay, so if suppose the value of the matrix 3x3 is 1, 2, 3, 4, 5, 6, 7, 8, 9, then you will have one vector 1, 2, 3, 4, 5, 6, 7, 8, 9.
Yes, right.
Okay.
So basically you want it to be applied to a neural network, because neural network is basically matrix vector multiplication. You want your output to be in the form of vectors. So that is why you do this flattening. And you use this convolution and pooling to reduce the size of the vectors. Otherwise you'll have very large vectors in other cases. So that is why those things are required.
What is the difference between artificial intelligence, machine learning, and neural network?
Oh, so artificial intelligence is like the superset of everything. It is so you want machines that can think like humans, that can create like humans. So that is artificial intelligence, a general term. Machine learning is a subset of artificial intelligence, where we have given this output and input. We have to learn the correspondence between this output and input. So machine learning is that part. There are other types of learning also. Those also come under artificial intelligence. A neural network is just a type of machine learning model. So this is you can say a hierarchy of those three techniques.
Okay, and where is the application of neural networks? What could
Oh,
be
so neural networks are, so basically the main problem is given some input, given some output. You want to learn a function so that you learn the pattern, right? So you have seen different algorithms, logistic regression, SVM. So neural network seems to be the better in all of best in as compared to all of these algorithms. So
how it differs
application
from
like
control?
uh-huh.
How it differ from control systems?
I did not get you.
How it will differ from control systems?
Oh, so I do not have much idea about control systems, but there are some applications of these control systems to maybe in robotics where we want to teach a robot how to hold something, how to work. The theory of control system also comes in that case along with neural networks or machine learning in that case. So I'm not an expert in control systems, so I cannot say how exactly it is applied.
In control systems also, the input and the fraction of output has been compared with the positive or negative feedback, right?
Mhm. So yeah, you can say yeah, it can be similar because here also you are looking at errors, right? Whether you are correcting, predicting correctly or wrongly based on that you have errors or no errors. So it may be analogous to that.
So what would be the pattern of the examination?
So I think the lectures are good. You should you can go through some of the books. I think I mentioned some of the books in an earlier lecture. Uh, so you can go through some of the chapters to get some. Most of the questions will be conceptual, as far as I know. So you try to get your concepts clear and practice some of these simple problems. I think it should be fine.
That is in the PDF, right? Video lectures,
Yes, yes.
recorded versions, right?
Yeah. So if you just search online for these topics, you'll also get some like different IITs have their websites, right? So you will find questions there also to practice. So you may try out those if you want more questions to practice. If you want more something to read to clarify your concepts.
Actually, this time a session I haven't been followed regularly. So will it going to repeat once again?
Or this, yeah, the course will be repeated next summer. Is I think this has been going on for I think 7 years or something. So it will be repeated again next summer. I think so because it happened in 2021. So maybe next summer or next to next summer.
Okay, thank you.
Anyway, the recordings are available on YouTube, so you can also go to that.
Yes.
So if there are no more questions, I think we can end the meeting.
I don't have any further questions.
Okay. Thank you. Okay, thank you everyone for attending.
Thank you.
Thank you. Thanks a lot. Well explained.